Synchronizing data, okay, that probably checks for a lot of folks here. We're here at SyncConf, and a lot of the things we want to synchronize are data. Across computation, okay, that might be different, or that may not be quite as obvious what in the world I'm talking about. So I'll sort of set the stage a little bit here. This is possibly what a lot of people are thinking about when they think about synchronizing data. You have a bunch of peers who all are thinking they have roughly the same type of data, and they're all trying to do stuff to it. They're all reading and writing and trying to just sort of stay in sync. We're not going to do that. Yeah. We do something very similar and very related, but I just didn't want to disappoint anyone who realized 15 minutes from now that this was not where we're going. We're going to do something that's, if you think of this as the right side of synchronization, like folks are writing, and that's sort of the main challenge, is making sense of their joint edits to a thing. We're going to be talking a bit more about the read side of the equation here. So the data is changing for some reason, and we, or you, in fact, have something you like to keep up to date as that data is changing. We're not going to think too hard about why the data is changing. Maybe there are 3 people jointly, collaboratively editing documents or data or what have you. But the challenge that we're going to look into is, as that happens, how can other people, potentially the same people, but also other people, not part of that group, stay up to date on some logic, some query, some view over that data. And I'm going to denote these, there's going to be some colors, and I'm going to think of F as just a placeholder for a thing you might like to think about the data. I'll give some examples as we go along, but hopefully you'll start to have your own examples too, because I won't be able to imagine them all for you. So, why might this be challenging? Surely, if you have a collection of data somewhere, you just like leap over and look at it and update F or something like that. That's probably now in sync. You've just updated it. But this doesn't scale, essentially, right? Like the actual challenge is you don't just have F of data. Some other person next to you is thinking about G of data, and it's different. And you're not in constant contact with them. You may not know who they are, might be on the other end of the world. And worse, some other jerk is working on H, and they're just going to use your output, not necessarily with checking with you either. Building on F and G and trying to produce whatever their derived data as a result. And you can imagine that if no one's actually thinking about synchronizing this data actively, if it's just you get what you get, it can be a bit of a mess, right? Like imagine F is a collection of data, and we want to sum up some number, some engagement score by user or something like that. And maybe G is counting the number of engagements per user, and H is like, I'm going to figure out the average engagement for each user. Taking the average when you have the sum of the counts for each of these things is pretty easy. You just divide one by the other. But if they're not actually synchronized and you're dividing numbers that don't connect with each other, you can get some real crazy stuff. Pretty obviously you can divide by 0. That's pretty easy. But also just dividing by a different number than is the number of terms in the numerator doesn't give you the average. It gives you some other crazy bit of nonsense. So how do you actually build on mud if you don't actually have numbers that make sense, that line up, that have synchronization? Synchronization is a sort of a foundational building block here. If you want to build up more information, views, derived knowledge, enriched data, sort of advanced data products, what have you, you're going to need, I assert, something like synchronization for everything just to make sense. And that's what we're going to explore in this talk. The ideal, what you might like if it weren't for the fact that you have issues like speed of light and stuff like that, the experience you might like is, as the data change, time freezes, the world pauses, some magical little pixies run around and update F and G and H immediately, and then unfreeze time, and it's as if everything just immediately ticked over from the previous version of the data and all of the derived results to the refreshed versions. We don't have that, but that's the experience we'd like to craft without the essentially without the behavioral synchronization. We don't actually want to force people to synchronize their experience, their passage of time for them. We want to synchronize the information and make sure that what they're looking at looks synchronized, even if we don't force them to all rendezvous and wait on exactly the same global block or something like that. But that's our goal. Our goal is to present as if the world changes in these nice ticks going forward, where everything's just always consistent. And the real world doesn't do that, as you might imagine. Speed of light, too bad. It just takes time to update some of these things. We're going to need to come up with a different notion of time moving forward. We're not going to rendezvous in real time. We're going to use a different concept. Concept goes back to the 1980s. Virtual time, you may not know it by this name, but I'm pretty sure as you see in the next few slides, you're like, this. First of all, this thing even has a name? That's crazy. But it'll be a concept that I hope isn't too surprising or alien. But I'm going to unpack it for you and show that this is like just a really nice foundation for building here. And it's non-trivial in the sense that there are a lot of people not doing this. So I'd like to make the case that this is a good idea, a good way to think about things, and also think about what it might mean to sort of attach onto or adapt this approach in work that you do. So great. So we have data turning into f of data. This is generalizes to h and other letters of the alphabet that come after it. But the rough explanation is very simple. Like you put it on the slides, and it's really just hard to explain why this is even complicated. So virtual time is the idea that what we're going to do is record with each of these transitions from initially A, then from A to B, then B to C, a virtual time. And it's a very fancy way of just saying, let's just write down as data a time, 0. Let's say 0, 1, 2. And we'll do the same thing with f of A, f of B, and f of C. I'll write down time 0, 1, and 2 as data. So a different way to think about this is it makes time explicit rather than implicit. Right? Rather than what do these things happen to be at this moment in real time, which would be an implicit understanding of time and relationships. We make it explicit. We'll write down as data time 0, time 1, time 2 for each of these things, and we'll try to use this as the foundation for synchronization. And if virtual time were real, we'd be done, right? Great, all right, we're done. We'll just march ourselves forward through virtual time and live our lives that way. Now, the awkward thing is that it is not real. Real time is different, and in particular, real time sort of flows like a bit of a wave on a beach or something. There's some lag. So real time is different from virtual time, and we live in real time. We have to sort out the fact that although we can describe the computation we'd like to have transpire in virtual time, we need to be able to go from real time into virtual time and then back again. And that's it's not immediately obvious how you do that. Maybe it is, and wonderful. I don't have too much to explain. But yeah, the real challenge is, although we can describe the computation we'd like to have, how do we provide that experience to people who are actually moving through real time? And let me just sketch how this doesn't have to be too problematic. There's an unlock for me, personally, which I'll try to reveal. But let's imagine we're at that red line that says real time. Right, so we've got B in the blue data at the moment, F of A in the green data. And first off, just virtual time has this appealing property that we can look at these two things, B and F of A, and realize these don't correspond. Right? B is at virtual time 1, F of A is at virtual time 2. They're not the same. Don't just hand these back to people and say, good luck. These are the right answers. But we do have to think about how do we get the experience of looking at synchronized moments in the data. And the virtual time paper, again, this is back in the 80s, so this is a while ago, had the observation like, great, yeah, reads will just be an event in virtual time also. So if you want to do a read, we'll pick a virtual time at which the read happens, and then pretend that that's how the world was when you went and looked at it. So nothing wildly complicated here, I think. We'll pick either time 0, time 1, maybe time 2, do a read, and show you the results for data and f of data at that virtual time. What are ways that we could pick these times? I'll just give you a few examples to point out that this is a policy decision, essentially, at this point. So if we're at that red line that says real time, the middle line there, we have f of A at hand. We also see that B exists. And we might imagine that C is on its way. We can answer the full results, data, f of data, at virtual time 0 if we want. That would be a bit stale. First, like we know A has passed already. This is not current, but it's consistent. And if you like a prompt response, that's a great virtual time to go and do a read at. If you like a slightly more fresh version, you can see that B is already in play. Maybe we should just hang out and wait for f of B. And this was, for me, the unlock, which feels very silly saying it out loud, but the unlock was realizing that one of a database's superpowers is just not responding to a query. Like, I want to see the data, and you say, like, not yet. We can't make the results show up any faster necessarily, but you're allowed to just chill out. Databases do this all the time. They just sort of hang out and wait for B to show up. And what that translates to is a bit of latency. Yeah, like the responsiveness gets worse. It's not as fast as it could have been, but it's fresh at this point, fresh and consistent, and that's appealing. And for various reasons, let me not talk about them here, but grab me afterwards. C is also a great thing to grab. If you go for C next, the next time coming up, you get a compositional form of strict serializability, which is appealing if you want to, in some sense, synchronize the readers. If we have two people reading, we want to make sure that they're seeing comparable things. A smart thing to do. The real thing to call out here, I think, is that this timestamp selection is essentially a local choice. You get to choose which time you pick. You get to decide, do you, in this moment, want to see, respond immediately, see slightly stale data, wait just a moment to see some fresh data, wait even a little bit longer to see information that you're sure other people are also just about to see. So you get to choose. This isn't a system decides for you. This is not a go contact the server and figure out what's going on type of thing. In the privacy of your own little computer, you get to decide what experience you're having. So personally, I think that's handy. In database lingo, this is people setting transaction isolation levels differently based on the needs of their applications. Yeah. What we've done here, to say it a different way, is we've turned what might have been a correctness problem, this inconsistency issue. If I showed you B and F of A, horrible, how do I even build on that? We've turned what might have been a consistency in my mind, a correctness issue, into a performance issue. So the real question is, when A transitions to B, how quickly can we go from F of A to F of B? Like, how long does that take? And if it takes a long time, this is going to be a pretty disappointing approach. Right? You get a lot of delay. And if it goes really fast, you really might not mind. And as it turns out, we're going to see there are techniques that make this go even faster than going to the primary source of data and asking it, what's the current value of F of B? Right, so the transitioning, the flow from A to F of, from data to F of data can be surprisingly fast. I'm going to sort of dive into that next. So yeah, incremental view maintenance, if you're not familiar, is an area of incremental computation, specifically usually with databases, that is designed around the problem of keeping queries or views up to date as data change, as fast as possible. The incremental part is the premise of like, hey, let's not start from scratch, that'd be crazy. We have the previous result in hand, we have potentially some hints about how we got the previous result. Let's try to go from an edit to the input to an edit to the output as fast as possible. Just in pictorial form, rather than think about B and C, we're going to think about B minus A, C minus B. These are the transitions that the data take as they go along. Unfortunately, in the picture, they're big. In practice, they're much smaller than A, right? The change, or the hope, fingers crossed, the hope that B minus A is actually really quite small. Not too much has changed moment by moment with your data. If that's not true, this may not be a good fit, but in a lot of cases, you might change a single user interaction score at any one moment, or a small set of them, what have you. And for this to make sense, we're also going to do the same thing for the output. Right? We're going to want to think about how the output changes as, how we go from F of A to F of B, and then how we go from F of B to F of C. And of course, it's very rare that you're going to be lucky enough to go directly from B minus A to F of B minus A. That'd be really cool. But too many computations just does not work. So what you end up having is B minus A, indeed, but you also have A and F of A in the background. So you can look at how you got from the previous thing to its output as a tool in getting from F of A to F of B minus F of A, and then so on with C. This is not easy generally. Like generally, queries are complicated and messy, but there's a certain class of them where life is pretty easy, and it lines up really nicely with the types of languages and constructions people use in databases and in big data tools and stuff like that, which are data parallel operators. And data parallelism, if you're not familiar, is a property of functions that allows you to slice the input to the function into a few different pieces. For example, if we were computing stats by user, the user ID is a key that allows you to partition the input data, and you just make a whole bunch of different little piles of your data sliced by user ID, and you can apply your logic independently to each of those slices, then put the results back together. This is the cornerstone of how a lot of big data tech work, is that you can partition up your data into these independent pieces and run them on lots of different computers. That was really cool. That allows you to bring a lot of computers to bear and solve big problems efficiently, but it's also the cornerstone of incremental computation here, where if A changing to B is small, then not too many of these piles change. Either a lot of piles just stay put, right? And if a pile stays put, it doesn't change. So if A1 is the same, A1 and B1 are the same, then F of A1 and F of B1 are going to be the same. It's just a property that data parallel operators have. if we're computing these aggregates by user ID and only one record is added with one user ID, that's the only pile that's going to change. It's the only number we need to recompute. Even if it's a complicated function, not the sum or average or any of these things, rerunning that even from scratch is a dramatically faster way to get to the right answer than redoing the whole of f. And concretely, it's a bit hard to make super general statements, but concretely, a lot of these things update in the orders of microseconds to milliseconds. Right? So these are the timescales we're talking about. The network round trips are the expensive things in these stories. Again, absolutely depends on what you're trying to do, but there are a lot of really good outcomes for people using SQL-style logic to express what they want. Now, when you actually need to go and accomplish a thing, your whole computation is very rarely data parallel, but it's made out of these data parallel building blocks, like joins and aggregations and filters and all these things are. These individual atomic operations may be data parallel, and they get composed into larger views, queries, logic, that are not themselves data parallel, but each of the building blocks being data parallel mean that the strategy applies to each of these moments in your larger your larger workflow here. You might need to reshuffle the data or change what the keys happen to be. But essentially, all of SQL maps down into operations that update relatively efficiently, or have the ability to update relatively efficiently. If you cross-join two massive data sets, I can't help you there. But we have access to efficient, sub-millisecond update times on your on a large class of SQL queries. So I'm just going to zoom back out from this and talk through where, I don't know, some positioning, let's say. Like we looked, in my mind, fairly small at these data parallel operators. We started to zoom back a little bit from synchronizing individual operators, Fs and Gs and Hs, as like joins and group bys potentially. But if you think about it, this is just one of your queries, right? This is a view. And you might have several of these. Like you're working with a collection of data, you're trying to accomplish a task, you're maybe trying to build up some refined data product or something like that. You've got several of these. And the exact same reasoning keeps all of these in sync as well. Right? So virtual time is providing access to synchronized slices through much more complex computation than just a join. They can all build on each other, and you can have now a whole bunch of synchronized, continually changing, sort of millisecond freshness experience here with more and more complicated operations. So we're really synchronizing potentially computation at this point. It's one of the ways of thinking about this as we zoom back out. But this might just be you. There are other people in the world. They may not be sitting right next to you at your computer working with you. You may not even know who they are. Right? So you think of these as independent teams of people working with data. And this ends up, you sort of keep stepping back out, and this is a very composable building bricks of how to share information, continually changing information, share it with other people, allow the virtual time information to flow downstream, and let people do whatever they want with it. Like again, a lot of this is very local positive in the sense that you're not returning back to data to check in and see, am I allowed to do a tick, or how do I keep these things going? Each of these sort of streams of updates tell you how to update your state without centralized control or coordination. And this is to say nothing, I haven't gotten into this yet, but all of this generalizes to arbitrary, uncoordinated sources of input data as well. We just need to introduce the concept of virtual time to each of them, or like as their changes are brought into the fold, make sure that there's an association between the changes that they're undergoing and virtual time. But then, yeah, in my mind at least, you have this very healthy building blocks that provide the firm foundation, at least, of being able to confidently say what you're producing out the other end. Like these are always correct results with a negotiable freshness responsiveness trade-off. And just to wind down with a few thoughts, but just to wind down. So virtual time, incremental view maintenance, a great combination. They're brought together to give you a nice consistent experience with performance characteristics that you get to choose the trade-offs for as you see fit. It's nicely decoupled. Materialize, for example, place I work, has a platform for building and managing a lot of these things, but you don't have to buy into it to use it. For example, a lot of, we have some integrations from Materialize into things like, for example, ZeroSync. Kyle did an integration into inside the 10 stack TV. So a lot of the information that is produced by this flow from virtually timestamped data outwards meshes really nicely with a lot of the local first, yeah, I want to get that information presented to people, and I'll handle that. Thanks very much. So these tools compose. It's not, there's no walled garden type thing going on here. I find that all of these pieces play really nicely together, which I'm a fan. A lot of folks have told us who use Materialize, for example, that there's this really empowering thing from their point of view also, which is that a lot of the complexity of wrangling all of this turns into just think about writing out the data. Right? All of the flow downstream of the data being always correct means that you don't have to shake out why are there glitches or inconsistencies here? Did you run the refresh job? All of that just sort of goes away, and you just think about, I just need to maintain the source of truth in a state that I want to look at. Right? However you like to do that. You use transactional databases if you like. You can use CRDTs if that works for you. But it dramatically simplifies a lot of thinking about how to operationalize these sorts of frameworks. And let me just wind down with, that's me, great. Materialize is place I'm at, and if you've liked anything you've heard about, there might be a few reasons. You can try it out. That's amazing. Feel free, but also we're hiring and stuff like that. So feel more than welcome to reach out. We have several folks from Materialize here too, and we're all delighted. I think delighted. Yes, no, sorry. We're all delighted to chat with just about any of you. If you have questions, you want to go deeper on any of this, we're not going to do it live right now. The questions. I'll do things around the break or off of the main thread of control, if you will. But I'm gonna stop there. Thanks very much.